briefly review Memtable and write flow innovations that Speedb introduced. First, a short intro about Speedb. So Speedb open source is a community-led project. It's a fork of RocksDB, fully compatible. We also rebase regularly to the latest RocksDB version. We talked to many RocksDB users to better understand if there are any pain points and what are they. And we discovered that these are the four areas that we should put a focus on. And today I'm going to deep dive in 10 minutes into one of these areas around the Memtable and the performance issue. So there was a repeating ask from the community to have extremely read and write rate for a single RocksDB instance. So we started to decompose the data path in order to better understand and identify the components that we might get improved. So the first one is the Memtable. So just a short reminder, Memtable is an in-memory data structure that serves both reads and writes operations, and it holds the most recent data. So every new read is first queries the Memtable before it goes to the cache and the disk, and every new write is actually first written to the Memtable. So let's see what we have today. Today with RocksDB, there are 5 Memtable. It's pretty much the same. We're talking about log n. The issue with Skiplist is that the lists are always sorted. So in case you want to insert a new element to the list, you need first to find the correct place to insert the data, and then insert the new element while keeping the list sorted. So this, of course, takes time, and every single operation is actually required seek before doing it. Even if you want to read element from the Memtable, you need first to find it in a sorted list. So again, we're talking about log n complexity. In addition to that, this is the log n complexity. It can be counted as an advantage. And also the fact that it consumes memory based on the data size and not more than that. But there is a clear disadvantage here that the writes cannot be 100% parallel. Since, think about it, if two writes, you want to write 2 different elements to the same sublist of the skip list, they will always have to wait for each other because it can't happen at the same time. So it's not 100% parallel. So we realize that we need to find an efficient data structure that serves very fast read and writes without compromising on seek. And of course, support parallelism. So Speedb introduced a new sorted hash Memtable. This Memtable consists of 2 data structures, hash table and array of vectors. The hash table built from 1 million buckets that are pre-allocated once the Memtable is created. And the vector can hold up to 10K elements. This is configurable. Also, the number of vectors is configurable and also depends on the Memtable size. So the combination of the hash table and the array of vectors, that's what gives us very fast read and write access while keeping the same performance for seek. And sometimes even better. So let's see how write operation works. So new writes are written unsorted, and we add pointer both to the hash table and to the vector, so we can use the vector later for seek. So the write operation is O1, same as, because we're using the hash function, so it's the same complexity of insert element to hash table. And there is a background thread that always keeps sorting the immutable vectors. So we have 1 million bucket. If you remember, I just said 1 million bucket in the hash table, and this is in order to reduce the possibility to have collision in the hash. And even if there are collisions, the performance are still better, and we'll see it soon. Also, the vector size is also pre-allocated. So again, the write operation is just O1. We just need to add a pointer to 2 different locations. Sorry. The read operation is pretty straightforward. It's just we're reading the data from the hash table, so it's O1. The seek operation, this is where the array of vectors came into the picture. We use binary heap, temporary binary heap, in order to sort the data. And remember, the data in the immutable vector is always being sorted in the background using this background thread. But in case it's not yet sorted, and also the active vector, we are using a binary heap in order to sort the data and only insert to the binary heap the elements that are in the range of the query element. Okay, so it's very efficient. It's very, okay. And so the complexity of the seek operation is basically depends on the number of elements in the vector, and again, this is configurable. So the advantages of the sorted hash memtable are pretty clear. We get very fast read and write access. This is O1. We get parallel writes, and also write doing seek operation is not blocked. The disadvantage is that it actually costs 8 megabytes more because of the 1 million buckets that we need to allocate, and this is per memtable. So this is just a short comparison between Skiplist and the sorted hash memtable from complexity perspective. So you see that from Skiplist, this is log n for all operations. For the sorted hash memtable, it's O1 for read and write, and we get log n for seek operation. And from memory consumption perspective, Skiplist has advantage because it consumes only the data size, and for sorted hash, it takes additional 8 megabytes. So let's see some test results. Here we compare mixed workload, and we see that we can get up to 25% more with the sorted hash memtable compared to the Skiplist, and for seek operation, we even get 13% more. But this was not the only bottleneck. We started to look at the write flow, and we found that there are 3 areas that we can improve. The first one is that the writes are written to the memtable, the first written to the wall before they're written to the memtable, for consistency matters. The second issue is that when writing to the wall, it uses append. Currently, it uses append writes, so it can only at a time write a single write batch. And the third issue that we found is that there are many times that DB mutex is taken on and off during the entire write flow. So we were running perf on a write operation with DB bench, and we found that 5% of the time the write flow is in a wait state, which is a lot. And also in some scenarios, you see that we get, with 8 threads, we get much more performance than 50 threads. So the parallelism is not working very well for all scenarios. So Speedb actually, we did 3 main changes in the write flow. The first one is that we changed the DB mutex with read-write lock. So we actually reduced dramatically the times that actually DB mutex is taken on the system. Writing to the wall is now not using append. We are writing to specific address space, so it allows parallel writes to the wall. And the third change is that actually new write is written to the wall and the memtable in parallel, so it also saves time and increases parallelism. So here you can see some test results. It compares the default configuration with and the memtable and the new write flow, and you can see that with the line above, I hope you can see it well. This is the new configuration with 50 threads compared to the red line at the bottom, which with the default configuration of 50 threads. And also we can see that the performance is better when the number of threads are bigger, as expected and not as we've seen before. That's it for today. I would like to invite you all to join our Discord and also check out our repo. There are very cool stuff there.